ladies and gentlemen. All right, so remember that this weekend you were asked to finish up to Unit 4. Okay, you were asked to finish up to Unit 4 because if I share with you the overview of trig, right? So this week we're going to cover Units 5 and Unit 6. All right, so we're going to cover 5 and 6, so applications of trig, and then we're going to look a little bit more into complex numbers. Right, we're going to cover these again. Each of them get 2 days. So today and tomorrow is Unit 5. Wednesday and Thursday is Unit 6 here. Okay, and then Unit 7 is, of course, our Semester 2 review and exam. All right, so if you're up to pace with me, right, that means you should be able to finish, if you really want to, the Semester 2 review and exam. You should be able to finish that this weekend and be totally done, okay? But of course, remember, if you're not up to speed, right, you still have all next week to finish and get that stuff done and turned in to me. Okay, so don't stress about it, but just know that there is an impending deadline that you have to be prepared for, okay? There is a deadline you need to be prepared for. All right, so quickly here to look at Unit 5. Okay, so to give you the overview of Unit 5, it is only 4 lessons. All right, and of course the 4th lesson being our unit test here. Okay, so really it's 3 lessons and a review section and a test here. Okay, and this is on the applications of trigonometry. Okay, so we've looked a lot at just how do things work, why do things work, proving that they work, and various ways of manipulating equations that we now know to be true in order to fit the situation that we have. Okay, so that's going to be the same here in this applications of trigonometry. Okay, that's going to be the same here for this applications of trigonometry unit. All right, we're of course going to take what we know and we're going to try to expand it a little bit or expound upon it in order to fit different applications. So if we start with this overview here. Okay, we've done a lot with right triangles. Okay, so now we're going to look at what happens when we go beyond those right triangles into those oblique triangles, right? So between 90 and 180. All right, and those triangles appear a lot more frequently than 90-degree angles in applications such as like navigation, surveying, industrial design, triangulation, right? They're a lot more prevalent than this perfect 90-degree triangle. Okay, so what we're going to see here is that in these oblique triangles, what we can do to solve for a lot of them is just try to find an easier right triangle within it, right, or beside it, right, something that we know how to calculate. Right, and once we know how to calculate, or once we find that right triangle that we know how to calculate, we can use a little bit of logic in our deductive reasoning to solve for the rest of it here. Okay. So of course, the trigonomic identities and formulas that work for right triangles, we're going to look at altering them. Okay, we're going to look at altering them in order to fit our oblique triangles. So let's take a look here at this quick overview. All right, so looking at something like the Leaning Tower of Pisa, looking at a ship, right? How do we look at the ship, the different angles there? Sure, alien travel, absolutely. Okay, airplanes, all of that stuff. So again, what they're trying to just show you here is that there are right triangles within the triangles that we see, or within the angles that we see. So if we were to look at these two people here, both looking at, let's say, the top part of the Leaning Tower of Pisa, right? We wouldn't know the angle because they're obviously, it's not a perfect right triangle. But if we were to make perfect right triangles out of both of those, we know how to solve for our right triangles, and we're going to talk about how to finesse what we know with right triangles in order to fit those different shaped triangles here. Okay, what we're going to cover today is the law of cosine and the law of sine. Okay, so of course our two best friends, cosine and sine here. All right, looking at our overview here, the first of two methods for solving oblique triangles is called the law of cosine. All right, and when we're dealing with cosine, it's really just a generalization of our Pythagorean theorem, right? Our a squared plus b squared equals c squared. Okay, and they're talking here about this thing called the Doppler effect. All right, and it's measuring colors of stars. All right. And using that and this property of the Doppler effect, they can estimate how far away stars are from Earth, right? So that's how they can say, oh, it's X amount of billion light years away, or things along that line. Okay, so they can use what they have, and they can use this law of cosine, which is just this generalized Pythagorean theorem, in order to solve for it. Okay, so if we were to look here, well, first, okay, you have this NOVA online if you're really interested in it, okay, and you can look, and it talks about what the Doppler effect is if you want to learn more about that. All right, but for this example here, we're looking at our star that is a certain amount of light years away.
Consider two stars, star A and star B. Star A is 35 light years from Earth, and star B is 40 light years from Earth. Viewed from Earth, the angle between them is 50 degrees. How could you find the distance between star A and star B?
Okay. So again, assuming we know the distance of both of these stars, that's what they're asking here. Assuming we know the distance of both of these stars.
To solve for the third side of this oblique triangle, you will need to use the law of cosines. You can prove this law because within this oblique triangle, there are two right triangles.
All right, and again, that is going to be the trick for all of these here that we're dealing with our applications. How can we make a right triangle out of these oblique triangles here? All right, and luckily for us, this one, if we go from star A straight down, right, it makes two perfect right triangles on either side of this new line here. All right, so let's take a look at what and how do we do that. Okay, so we got to remind ourselves, of course, Pythagorean theorem is a squared plus b squared equals c squared. All right, but if it's not a perfect right-hand triangle, so if C gets larger or smaller, what happens to our quantities of A and B, right? What happens to our quantities of A and B? All right, and what we can say here is we can actually say a lot. So if we look at increasing our C, right, that's talking about making our C angle here longer. And look, if you notice, it moves that triangle. All right, if we decrease C, we're going to shift C more towards this way and look at it as a smaller than 90-degree angle. All right, but let's look at first if we increase our value of C here. Okay, so as we increase this angle, our length of C is also going to increase, right? We're making this a larger angle, and C has to get bigger. All right, and so then what you can notice here is that we've changed from an equal sign to a less than or equal to sign. All right, because as we make C much longer, A and B may not be able to keep up. All right, so A squared plus B squared will be less than the square of our hypotenuse C. All right, if we decrease C, right, if we shift this, okay, and we don't change A or B, and I guess I should have mentioned that's a thing here, we don't change our A or B, okay, we're going to notice here that C has to get smaller. All right, so then this changes to A squared plus B squared is greater than our C squared. Okay, so we understand a little bit about how this changing of our angles changes our Pythagorean identity. All right, it changes from being equal to being greater than or less than, depending on the angle. okay? And what we can do here is we can say for any triangle with ABC, and it has those side lengths, okay? And of course, they're opposite, all right? Let me just take a second to digest this with you, okay? So if you have triangle ABC, okay, the capital letters are talking about the angles, okay? So obviously this would be angle A, this is angle B, and this is angle C. And when we're talking about side lengths, okay, that's going to be lowercase letters, and that's what's going to be opposite of each angle. So if I look at angle A here, length A is small a across from this, all right? I have angle C, it's going to be lowercase c across from that angle. Okay, so that's going to be really, really important moving forward in case they don't label all 6 of these letters here. Okay, but regardless, whenever we shift both of those angles, here, we can use this relationship, a squared plus b squared minus 2 times AB cosine of big C equals C squared, okay? And obviously we'll talk about how we got here and why this works in the next couple of slides here, but notice that it looks similar to our Pythagorean identity, obviously with the addition of this minus 2AB cosine C term, okay? And again, highlighting that lowercase a, lowercase b is talking about side lengths, and this capital C here is talking about angle, okay? It's talking about the angle. And it works for both of them, right? Whether we're getting larger or smaller, it works for both of them. All right, and what we're gonna do here is we'll talk about obviously why. All right, so we need to take a second here to make sure that it even makes sense, this minus 2AB cosine C term, okay? So let's take a look at why does this make sense? What does that term actually stand for? All right. So when we look at our normal unmodified Pythagorean theorem, apologies. All right. If we were to look at our Pythagorean theorem for our 90-degree angle here, okay, we would normally just write it as you see up top. If we want to modify it using our law of cosines here, okay, our law of cosines here, what we're going to notice here is that cosine of C would be 90 degrees, right? This is 90 degrees here for that capital C. And so when we actually do out this bottom calculation here, we're going to notice that cosine of 90 degrees is actually 0, right? If you remember our unit circle, cosine of 90 degrees gives us that value of 0. All right. And so it doesn't matter what the side lengths of A and B are, because negative 2A times B times 0 is going to cancel that term out. So we're going to be left with here just A squared plus B squared, right? And then that turns our left side of the equation into our normal Pythagorean theorem. All right, so it works here for our 90-degree angle. All right, and that's obviously a good step here. But now let's take a look at what happens if we're looking at something maybe over 90 degrees. Okay, over 90 degrees. All right, so what we said here is that we know that if we don't have this corrective term here, all right, that C becomes larger, C squared becomes larger than our A squared plus our B squared. All right, so in order to account for this term here that we have to add has to be a positive number. It has to be a positive number because right now it's missing length in order to equal C squared here. So we've got to add a positive number. All right. And what happens here, again, remember your unit circle, that if C is greater than 90 degrees, right? Our unit circle, imagine. Let me see if I can draw a circle here. Perfect. Hold on. All right, one more. All right, so taking a second here to remember what our unit circle looks like. Okay, so again, our unit circle here, this is starting at 0 up to 90, 90 to 180, 180 to 270. All right, and looking at obviously this upper right hand one is quadrant 1, then quadrant 2. All right, and then bottom being quadrant 3 and quadrant 4. All right, but if we look here, what this is saying is what this is saying here is that when C is greater than 90 degrees, right? So typically we're going to stay in this region here, okay? It's in this quadrant 2, all right? It's in quadrant 2 here, all right? And in quadrant 2, we're dealing with our x coordinates, apologies. When we're dealing with cosine, we're dealing with our x coordinates, all right? And so since we are in quadrant 2 dealing with cosine, right, that means that our x values or our cosine values are going to be negative, all right? So in quadrant 2, cosine is negative, all right? But that's going to be great for us because if you notice here, we've got a negative sign out in front. So we need a negative to cancel with a negative in order for this overall term to now become positive, right? And again, since we're dealing with over 90 degrees, we're in quadrant 2, we have a negative value. Negative cancels with negative. It gives us that positive value that we need in order to make this law of cosines true, okay? So that makes sense for us in this case. All right, now oppositely here, if we look for C of less than 90, okay, so we're going to be dealing with quadrant 1, okay? So since we're dealing with quadrant 1 and we're dealing with cosine, our x values are going to be positive, all right? And since our x values are positive, when we have a positive cosine multiplied by a negative number, it means this overall term here is going to be negative, all right? And let's see if that's what we need. Right, and remembering what we talked about earlier, when we shift this to be negative, a squared plus b squared is now larger than our c squared value here. Right, it's now larger than our c squared value. All right, so in order to make this actually equal to each other, we need to make this left-hand side smaller, right? So we have to subtract a value from it. So the fact that this term here is negative makes this expression here true, because this is going to decrease our a plus b and bring this back towards equal. Okay, bring that back towards equal. So right now this makes sense to us. Okay. Ooh. But now if we go back to looking at the distance between the two stars problem, okay? The reason we could do this is because of this thing called our distance formula. And I know we've talked about it. I can't remember exactly when or which class, so I apologize here. But we've definitely talked about this distance formula here, all right? And effectively, this distance formula is just a version of Pythagorean theorem, okay? So if you look at this here, this distance formula, it's talking about how long this distance is here when we're dealing with a vertical and a horizontal change, okay? And so in order to do this, what we can do is, again, take a version of our Pythagorean theorem. So if you assume that this is distance x, this is distance y, right? In order to calculate d, we would take x squared plus y squared, and then that would give us our d squared. In order to get d, we'd have to take the square root of both of them, okay? And effectively, that's what we do here with this distance formula. except for we don't have this as one set value of x and one set value of y. So what we have to do is we just have to take the difference between 2 points. So we go x2 minus x1, and we do y2 minus y1, right? But then effectively, this is a version of our Pythagorean theorem, right? We have the square root because we want to get d instead of just d squared. Right, but if this was d squared, it would basically be d squared equals x squared plus y squared, right? It'd be something that you're more familiar with. Okay, so it's just, it should be pretty simple, hopefully, or easy to remember here because it's a version of the Pythagorean theorem. All right. So if we look at then, of course, doing this calculating distance problem, okay, we knew star A, we knew the distance of star B, and we were trying to figure out the distance between both of them, okay? And the first step, I think, would be and so does Apex, I guess, would be to orient them, okay, on an XY plane, all right, to put them on an XY plane, because if I go back and then forward here, all right, notice it's a little bit more difficult to realize our right triangles here, okay? So in order to do this, it's easier if you orient them with the axes, especially if you can do it with the origin value here. So it's saying right here, orient it so that x is at the origin and the angle is in a first quadrant angle. All right, so perfect. Okay, we make Earth our origin, and we have it being on our XY plane here. All right, and then knowing this, okay, what this does here is it gives us 2 set points that we now know. We now know that Earth is located at 0, 0, and we know that star B is located at 40, 0. Again, 40 being 40 light years. Okay, and then since we know that we can split this into 2 right triangles here, sorry, we can split this into 2 right triangles here. All right, we definitely know the distance of, we know the angle of here is 50. Okay, we know that this is 50, and so what we can do here is, knowing that this is 35 light years and knowing that this is our angle, we can use our definitions for sine and cosine to figure out our coordinate where star A is going to be. All right, we know where star A is going to be. And if we look at the calculation here, of course, it's cosine of 50 is equal to the adjacent over the hypotenuse, and sine of 50 is equal to our opposite over hypotenuse, right? And then since we've got our x and our y, right, it's x over 35 and y over 35 for both of these here. We just multiply our 35 to get it by the other side, and that's how we get in our x and our y coordinate by itself. Okay, so some simple replacement, and then algebraic multiplication here. All right. And now we know our x and our y coordinate for star A, okay? And since we know our x and our y coordinate for both star A and star B, we can now calculate the distance between them using our distance formula here. Okay, so we can now calculate the distance between them using our new distance formula. All right, again, setting star, it looks like we set star A, okay, as x1 and y1, and we set star B as x2, y2. So if I back that up a little bit here, all right, star A is got set as our first distance, and star B is our second distance, okay? And the reason they chose that is just based on position on the x plane. All right, so they set star A equal to x1, y1, and star B equal to x2, y2. All right, so now knowing that, it's just a simple replacement here. And, it's just a simple replacement here. They follow through with algebraic terms. All right, they follow through with algebraic terms. Again, canceling out or replacing where they can. All right, and then finally, when it gets boiled down to here, okay, they can use the Pythagorean theorem to simplify this term. All right, so they use Pythagorean theorem to simplify the term. Thus, C is equal to this guy here, which is equal to approximately 32.10 light years away. All right. So another thing they did here was they said you could simplify this guy here, again, using the Pythagorean theorem. Because cosine squared and sine squared, if it's the same value, that equals 1. All right. So they're assuming that you picked up on cosine squared plus sine squared equals 1. So that was just a replacement value. Or what I would just suggest is if you get it down to this point here, okay, if you get it down to this point here, you could just plug this entire thing into your calculator. Okay, you could plug this entire thing into your calculator. As long as you are conscious of signs, that's all that matters. All right. So again, I don't know if I would have done this step that they did, but again, the reason they got this is because it has the same angle. It has the same angle. And what they were able to do is they factored out a 35 from both. They were left with cosine squared plus sine squared, again, of the same angle. And using our trig identities, that's going to give us a value of 1. Okay. But regardless of if you plugged in here or plugged in here, it would give you the same answer of about 32.10 light years distance. Okay. So if we were to look at in general, okay, so once they got this simplified version here, if we were to relabel, okay, using our new value that we found out, okay, what we could do here is realize that the final expression that we came up with to calculate for distance C is just equal to our C squared is equal to A squared plus B squared minus 2 times A times B cosine of C, right? So it just gives us our law of cosines, okay? So again, this is another way of showing that, hey, we did it the way that we know, and we still end up with this same expression, right? So again, proving that this expression is true. All right. And speaking of proving here, we're going to go through the proof for cosine. Okay, we're going to go through the proof of cosine now, talking in general terms here.
Consider a general oblique triangle. Label and then place the triangle on the xy plane so that vertex C is at the origin.
Okay, so that's going to be important, all right? Making sure that vertex C can be at the origin. Okay, vertex C can be at the origin. And that's what that's going to do is, again, it's going to keep everything in this quadrant 1 here. All right, and it's going to give us a point of 0, 0 for C, and at some distance A, 0 for this other point here. Okay, assuming, of course, that this is angle B. All right, and now that we know that, when we divide and we do our right-hand triangles, okay, we know based on our identities here that our coordinates for our A is going to be B cosine of C and B sine of C, again being X and Y respectively.
Now calculate the distance between points A and B using the coordinates and the distance formula.
So again, doing it generally. Okay, they're plugging in general values for you here to calculate this distance C. All right, where of course it's X minus X, and then that's going to be squared plus Y minus Y, and that value is going to be squared, and we're going to take the square root of it.
This calculation proves the law of cosines since you can square both sides of the equation.
Right? So going from our simplified distance formula for C, if we square this, this gets us to this law of cosines. And again, because we've changed our equation to look like our law of cosine, we had then proved that this works.
Consider again the triangle you started with. What would happen if you oriented the triangle differently in the XY plane by choosing a different vertex to be at the origin?
Okay, so instead of having C at the origin, let's put A at the origin. All right. What we can then notice here is we can still calculate a value for C. All right, we can still calculate our XY coordinates for C. We can still make a right triangle. Okay, we can still make a right triangle here. All right. And we can calculate this distance between point B and point C here. All right, still using our distance equation. Okay, and using our distance equation, we still get our sort of looking formula for our law of cosines, right? There are some slight differences here, but hopefully you notice that it's looking very, very similar. All right, and again, the reason we had to find this right triangle here, was because we had to figure out what the coordinate x, y for C was, right? So using this right triangle, it helped us figure out everything in terms of our x and y coordinates using this angle A, right? Using angle A. All right, if we look at putting B at our vertex, okay, now our angle shifted far out this way, but again, we can still make a right-hand triangle. We can still use our distance formula here to calculate our value between C and B. Oh, sorry, or between between A and C, right? We could calculate both of these, but I forgot we are missing that value there. All right. But if we want to calculate the distance B here, right, between these 2 points, okay, if we want to calculate our distance B here, we still then use our distance equation, we solve, and again, it implies this sort of familiar looking equation here. All right. And what this tells us here is that depending on what we choose and what we're looking for, we can modify our law of cosine into one of these 3 forms here. All right, one of these 3 forms. So if we're looking for A squared, right, we're looking for this distance of A squared here. All right, it's going to be B squared plus C squared minus 2BC cosine of A. All right, minus 2BC cosine of A. All right, and what I want you to notice here is that it's always 2 terms that are squared that are added together. All right, then it's going to subtract 2 times 2 of the sides and cosine. All right, so there are a lot of similarities here. All right, and for B squared here, all right, you replace B. Anywhere you see B, you replace it with A. Anywhere you see A, you replace it with B. All right. And again, what you should notice is you've got, in order to solve for B squared, A squared plus C squared minus 2, now times A times by C, cosine of our angle B that we're looking for. Okay. And obviously that pattern holds true if we're looking for C squared. Okay, you've got A and B squared added together minus 2 times AB cosine of C. All right, so those are 3 forms of the same equation. Again, I think they're pretty easy to understand how you get there. So you don't have to memorize them, but just realize that there is a pattern to it. All right. So if we were to look at the kind of complete forms of these here, so if we're looking at, again, capital letters talking about our angles, lowercase letters talking about our lengths, all right, we can clearly see in this standard form here, the 3 forms that we just saw, and what they're saying is alternate form. So this is looking at if you're solving for a length, and this one's looking at if you're solving for an angle. Okay. And this is, of course, again, solving for a length in standard form, and your alternate form is solving for an angle. All right. And what that's going to be dictated on is obviously what information do you have? Okay. What information do you have and what can you solve for? So if we look here, all right, it says consider the 2 stars. We knew the distance of star A and star B. And we wanted to figure out this third distance here. All right. So obviously we already did this problem here. And we know that we have to use this equation here. All right. And problems like these are called SAS. And the reason it's called SAS is because it stands for side angle side. All right. Side angle side, right? We knew a side here. We knew our angle and we knew a side. So this problem is called a side angle side problem or a SAS problem. All right. And so when we're dealing with those kinds of problems, okay, we can use our law of cosine in its standard form here. All right. If we have a SAS problem, we can do our problem in its standard form. All right, so looking at another example of an SAS triangle, okay, Tom's route from his house to school consists of 2 straight lines. First, he drives straight for 6 miles, then makes a right turn at 60 degrees, drives another 8 miles. So again, you have a side of 6, you have an angle of 60, and a side of 8. How far is Thomas's school from his house?
You know that Tom drives straight for 6 miles. Then he makes a right turn of 60 degrees and drives another 8 miles. Implicit in this problem is an oblique triangle whose longest side has Tom's school and home as its endpoints.
Okay.
Call that distance C.
Awesome. All right, and let me point this out here. This is a really, really good thing you should do in general when you're dealing with word problems, especially when we're talking about trigonometry here. Okay, draw a picture of what the heck this is saying here, so that you get an idea as to what triangle you're dealing with, right? You don't have to draw a house. You could just write the word house, but realizing that, hey, I go 6 here, then I turn and I go 8 there, right? And understanding what that means.
After 6 miles, you know that Tom turned right 60 degrees. Thus, the supplementary angle must be 120 degrees.
Okay, and knowing that that is also the last thing here. Remember, when you add both of these together, if it makes a straight line, both of these angles have to equal 180. Okay, so since we knew he turned at a 60-degree angle, all right, and when we're talking about turning here, right, he's going straight, and so his car turned 60 degrees. So we're talking about that angle there, right? So that angle would be 60 degrees. Okay, therefore, the angle on the actual inside of the triangle would be 180 minus 60, which is how we get that 120. All right, but this is the picture that we're dealing with here. So then the question is solving for side C here.
Using the information given, it is clear that this problem is simply asking to solve for the third side in an SAS triangle.
Okay, so the distance from Tom's school to his house is approximately what? And I'm just going to choose an answer at random here. Obviously, you guys would actually plug this into your calculator here. And again, you would have a squared plus b squared here, or b squared plus a squared, doesn't really matter, right? But you'd have 8 squared plus 6 squared minus 2 times 8 times 6, right? 2 times ab times by cosine of your angle C, right? And again, C has to be the angle inside of our triangle. So that makes it that 120, not the 60 degrees, okay? So effectively, side angle C here is 12.17 miles.
Now that you know the length of the third leg of the triangle, you can find the other 2 angles. Try to do this on your own, using the alternate form of the law of cosines. Press the C calculation button to check your work.
Okay, so again, now that we have all 3 of these angles here, okay, she said it, you can use the alternate forms of law of cosine. So if we look at our calculation here, okay, if we look at our calculation, so we would use the alternate form. So something where we have cosine of A equals whatever, right? Or cosine of B equals whatever. Okay, again, what it's going to do is it's going to take it and rearrange the equation in order to solve for your cosine of A. All right, and once we get cosine of A equal to a value, right, we plug in our inverse cosine. Remember that cosine -1 means inverse function. all right? And the inverse function on your calculator is that second, and then you hit the original function button on your calculator, right? So to get that, you would hit second cosine in order to get cosine to the -1, all right? And assuming you're in radians or degrees, right? Whatever your calculator is set to, once you hit that, it'll give you out either 0.45 radians or this 25.78 degrees, okay? Either of those work. And then you can either re-go through this process again to figure out the third angle, or just know that a triangle has to equal 180. So you take 180 minus the two angles you already know, and that gives you your third angle. All right, so that's a way of solving for this here. All right, then finally, another use of this is if we're dealing with something called an SSS triangle. So you can probably guess it, it means side, side, side triangle, right? So you know all three sides, you have no idea about the angles. All right, so in order to solve for this here, okay, what you're going to do is you're going to use the alternate form of cosine. So let me choose an answer at random. All right, and looking at this here, remember, you have cosine of C is equal to, and you have this equation here. And again, if you don't remember that off the top of your head, that's fine. It's a standard equation that would be given to you, or you have at your disposal. All right, but once you have that here, all you have to do is plug in your values, right? So you have to plug in your values and then solve. All right, and this is where it becomes super important, is knowing which value you have to subtract and which value you're going to add. So remember, if we're subtracting C squared, C, lowercase c, is the side that is opposite the angle, okay? So side C here is this 4. So that's the only thing you have to be really careful about. All right, once you have the right equation, make sure you know what is what length, or which length stands for which letter. Okay, so then if we have cosine of C is equal to our 0.91, okay, this is of course where we have to plug in our inverse function. So inverse cosine is equal to our 0.91. And again, depending on what your calculator is in, it'll either give it to you in radians or it will give it to you in degrees. All right, and if it's reported out in radians, you can convert to degrees by doing, again, the 180 degrees over pi radians. All right, so that would be, we could do that, and that would give us our side measure of angle C. All right. Then if we wanted to do side A, guess what? We would do the same thing again, right? We would do the same thing again, but we'd solve for cosine of A this time instead of cosine of C. All right, again, paying attention to which values are added or which are subtracted. But once we've gotten that, again, we plug in our inverse cosine, we can then figure out our side angle of, our angle of C. Okay, and then finally, since we've got 2 out of our 3 angles, we can just take 180 minus both of those angles, and we can figure out our third easily. All right, so that would be our side triangle. Okay, and it turns out there's many real world situations where this is really, really important here, and one of them is a navigation. All right, so if we are piloting a ship in Singapore, we have to unload at dock A and another at dock B. Okay, so we have dock A, we have dock B, and when leaving dock A, you have to proceed directly to a buoy represented by point C. Okay, so we have to go from dock A to point C. From there, we've got to go directly to point B here. All right, we know the distance between dock A and dock C, and dock C to dock B, but how far away is, we could ask how far away is dock B to dock A? Well, across land, we know that it's 6.6. And then the question is what degree of turn do we need to make at this buoy? all right? So again, now that we have all three of our sides, right? So this is a side, side, side triangle. This is going to ask what is our angles here? So what kind of a turn do I need to make at point C? All right, and again, with cosine of C, we just use our alternate form of cosine. We solve for cosine of C equals a value. Then we're going to use our inverse function, and it's going to give us our answer in radians. There we go. All right, so it's going to give us our answer in radians. And then what we can do is we can now convert that answer from radians to degrees by using the 180 degrees over pi. Okay. And again, I know I'm flying through that quickly, but take a minute to go through that and actually double check your calculator on that. All right. But we know, apologies, let me go back here. All right, so we know that this has to be a 53-degree turn. Okay, so a 53.29 degree turn. All right, and just like the car example here, we know that it has to turn 53 degrees. Okay, so we have to turn 53 degrees. All right, so the degree that makes up our turn here, okay, is going to be 180 minus that turn. Okay, so it's going to be a 180 minus this degree here. All right, because again, when we solve for our angle, we're talking about our inside angle here. All right, so when we're talking about our angle, right, it's obviously the angle inside the triangle. All right, but just like the car problem, when we're actually talking about what we are turning, okay, that has to deal with the angle outside of the triangle. Okay, so it has to deal with the angle outside of the triangle, because if we don't make this turn, we would continue on this dashed line here. All right, so in order to get from this dashed line to this green line here, we have to make a 126.71 degree turn. And the reason we got that is, of course, because we had to do 180 minus the angle that we now know is inside of our triangle. Okay, so our angle is 53 degrees, but our turn, if we're asked for the degree of the turn, it's 180 minus 53, which gives us this 126 here. Okay, so then if we look at a summary of these values here, we've got our side angle side, or our SAS triangles, and then we have our side 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 triangles, or our S triangles. Okay, and in general here, again, for side angle side, you're given the length of two sides and the angle between them, right? So side angle side, and then for side side side, you've got all three sides and no angles. All right, but regardless, both of them, you can use the law of cosine to solve. You're just either going to use the standard form or the alternate form. Okay, you're either going to use the standard or the alternate form. And obviously here they show our side, side, side here as the one step further. Same thing here for the side angle side. They showed this taking the square root. So there is a slight modification between those general forms that you saw and those. Okay, but I will let you guys practice these for obviously tonight before you take your quiz here. So go and make sure you can practice those and you've got them correct there. All right, looking forward at this study sheet here. Okay, of course, the main one is understanding the law of cosine and knowing the difference between its standard form and its alternate form, depending on which side we are looking for. Okay, so having this handy is going to be a key here. All right, and then making sure that when you solve the problems that we worked through in class, that you can actually get the values out on your calculator as well. You have to make sure that you have no major calculator errors. And again, the key for me is making sure what mode your calculator is in. Are you going to solve for radians or are you going to solve for degrees? And that's, again, of course, dependent on the mode of your calculator. All right, then side problems, you're going to use the alternate form of the law of cosines when you're solving those, so keep that in mind. And then, of course, remembering that your 3 sides equal 180. So once you get 2 of your sides, all you have to do is take 180 minus both of them, and you can get your final angle out, okay? And then here, the last reminder was, when you are talking about this, really make sure that you have a nice picture in your mind or on your sheet here as to what you're looking for, because again, it asked what degree of turn does the ship have to make, right? Well, we figured out the angle inside of the triangle, but it asked us what degree turn does the ship have to make. So knowing that just because I calculated out the value, I wasn't finished. I still had to go one step further. So really, again, making sure you understand the difference between those. All right. So then quickly looking at the checkup, obviously it's going to be a good idea for you to work through some of these problems here. Of course, again, formulas are given to you, but basically with a lot of these problems here, especially these first ones, it is all about drawing a picture or looking at the picture and understanding, are you dealing with a side angle side or a side triangle? All right, and then based on what you have, right, same thing with here, based on what you have, draw a picture, figure out what triangle you're dealing with, and then figure out the appropriate equation you're going to use. And then it becomes just a plug and chug problem. I mean, with basically all of these here, it becomes a plug and chug type of problem. Okay, and then obviously with the word problems here, it becomes a little bit more difficult, just slightly. All right, again, the trick that I can suggest with these is that when it tells you what's going on in words, draw a corresponding picture. Okay, that's going to be the most helpful thing. Draw a corresponding picture, because then you know exactly what you're looking for, and it should be a little bit easier, hopefully. Okay, moving forward here into the law of sines. Okay, so it's going to potentially have some similarities, but also some differences here between the law of sine and the law of cosine here. All right, and obviously, the law of sines is our second way of solving problems that don't have right triangles, right? So they're non-right triangle problems, all right? So if we look here, we could say sine of A over A is equal to sine of B over B is equal to sine of C over C, all right? And this is what our law of sine states, all right? So this is what our law of sine states for both triangles, whether they're greater than or less than 90 degrees, all right? So to put it another way, the way that they say it is the ratio of the sine of the angle to the length of the opposite side is the same for all parts of the triangle, right? So there is a ratio between sine of an angle and its corresponding length, right? And that's going to be equal for all angles and sides, right? So that's what it's going to say here. All right. So if we look here, we'll take a look at why it makes sense in the first place. All right. So again, looking at a right-hand triangle, we have sine is equal to the opposite over the hypotenuse, right? So A over C. All right. And remember, any number divided by 1 is the same number. So if we have C divided by 1, right, that gives us a value of C. All right, and we know that sine of 90, right, if this is 90 degrees, right, we know that sine of 90 is 1, right? We know of sine of 90 is 1. All right, so we can rewrite this and say that our angle here for C, right, what we can do here is if we're looking for C, we can say C is equal to C over 1, right? That's just a way of saying C is equal to C here, all right? We know that sine of 90 is equal to 1. So we can replace 1 with sine of 90, and we get C over sine of 90 is still going to be equal to the value of C here. All right. And then our final replacement, all right, our final replacement here is we know that sine of 90 is sine of angle C here, right? It's sine of angle C here because we're dealing with our 90-degree angle when we're talking about this guy, all right? So combining these facts here, what we can do is we can say, all right, C over sine of C is going to be equal to A over sine of A. All right. And we can do the same thing for B here, right? You can go and prove that this works for all of the sides, right? We can prove that this works for all of our sides. All right. So if we look at, again, we showed it with our right triangle. If we looked for obtuse triangles, okay, we can see the same thing here. All right, we can see the same reasoning, that it's still going to work out based on our triangles here. Except for the fact that our equation here, if we increase our length, okay, our equation C is equal to A over sine of A is no longer valid, okay, because length A has changed, but not C or sine of A, okay? So it has a slight modification here. So in order for this equation to be true, you can compensate for the change of length by multiplying the left side by 1 over sine of C, okay, 1 over sine of C. All right, with an acute triangle, okay, with the acute triangle, same thing, 1 over sine of C. All right, so now if we look at actually proving this law here, right, proving this law, okay, we can start with a non-right triangle like this one, all right, and it's really nice that they already have B orientated with a horizontal axis for us, okay. So what we can do then, I don't know why they would do that one, that's funny, but they wanted to draw a line segment from this corner C to the opposite side in order to make a right triangle, right? Or technically two right triangles here, okay? And this segment is known as the altitude of the triangle, all right? And we can now assign this its own length here, K. So if we look at this here, all right, with this new right triangle that we just drew, all right, we can see that sine of A is equal to K over B, all right? And sine of B over here is equal to K over A, right? Again, using just our normal identities here. So if we were to use and solve for B in both of these, what we can figure out is that B sine of A is equal to K and A sine of B is equal to K. So we can then set them equal to each other, use a little bit of algebra, and we have part of our law here, right? So again, if I were to divide both of these sides by sine of its value, right, I can move sine of A over here and sine of B over here, and this is how I get my law of sines, okay? Then if we were to draw another right-hand triangle, right, dividing this in half here, we can have this label, this length B value M, all right? We can have this length B value M. All right, and then same thing here. We solve for sine of C and sine of A using this new value M. All right, again, set them both equal to each other, and A over sine of A now becomes equal to C over sine of C. And since C over sine of C is equal to A over sine of A, it's also got to be equal to B over sine of B, since that was the first part that we discovered there. Okay, so that's again a good way of showing this here. All right, but obviously we know that triangles aren't always right-hand triangles. especially if we're looking at our different types of problems here. All right. And now we're going to add a third type of triangle, right? So not our side angle side. So SAS was side angle side. SSS was side, side, side. Now this last one here is called SAA. So you can probably guess it's side, angle, angle. All right. So if we look here, we've got a side and then two angles. So side, angle, angle. All right. So assuming we need to find the value of X here. Okay. Assuming we need to find the value of X here. All right. It is referred to as a side, angle, angle. Okay. And we are, again, it's specific because you're given the measures of two angles and the length of one side not located between the angles. All right. So again, if we were solving for X being here, this would be a different problem. So it has to have X outside of those two angles. All right. And so what we just do for this here is we set this problem and we have side over its sine of its angle, right? So when we do this here, we can set this as A and B or C and D, right? It doesn't really matter as long as you're consistent here. So what we do is we match up the side length with its opposite angle and we get this equation here. All right, so X over sine of 40, right? So X over sine of 40 and 10 over 120, all right? And then we move sine of 45 to the other side in order to isolate our X value here. All right. And then one of two things is going to happen. Okay. First, you can do what they did. If you're asked to give an exact answer, all right, you would have to use your knowledge of the unit circle, right? And realize that sine of 45 is square root of 2 over 2 and sine of 120 is square root of 3 over 2, right? And then you would simplify the way that they did. Or if you were asked to give an approximate answer or you know, you could calculate it out. If it said calculate, you could plug this directly into your calculator and get out a decimal value here. So it'd be 10 point something, okay? So you could get out a decimal value there. All right. They're also saying you could have easily just found out that this was 15 degrees, okay, or easily, right? We could easily find out that this is 15 degrees because we do 180 minus 120 minus 45, right? And we call this side angle Y. Okay, perfect, right there. So side angle Y. All right. So again, to figure this out, we could use our law of sines, but now, of course, we have to eliminate this 45 degrees and use this side of 15 degrees, all right? But doing that, again, it's a simple replacement into the equation and solving straightforward, okay? So once we do that and we use a little bit of algebraic skills here, again, not anything new to us, we use a little bit of algebraic skills and we get an exact value here, or of course you plug it into your calculator and you get out this decimal here. All right, so both of those answers are acceptable. It just depends on what you're being asked to do. Remember, exact values are asking you for, you know, they're asking you to write it in terms of square roots or fractions, right? All of that stuff. But when it's asking you to calculate, it's asking you to actually put it in your calculator, hit enter, and get out a decimal value that you then round to. Okay. So then if we look at another one here, okay, we're dealing with angle side angle. So this is a different type of triangle. And hopefully you're picking up now that if you look at the triangle, and it's a certain type of triangle, you can only use certain rules. So again, if you're dealing with an angle side angle, you're going to be dealing with our law of sine versus our side angle side, you'd be dealing with cosine. Right? So hopefully you're picking that up here. All right. But if we look at this new one, an angle side angle, let's take a look at what that means here. Again, a familiar problem of our tree and our shadow. Okay, so again, we were able to make a right-hand triangle. but it's saying, what if the tree's not grown perfectly straight up? What if it's not a perfect right triangle here? Or it's breezy and it's pushing the tree at an angle. Can we still find the height of the tree? The answer is, yeah, absolutely, right? Absolutely. So if we know height h, okay? Oh, sorry, we're trying to solve for height h here, okay? We know that this one was 40 degrees, or we estimate it to be about 40 degrees, all right? And we are able to estimate or about measure, right, the length of the shadow here, okay? The final thing we would need to look at is obviously the angle that the tree is resting at, okay? But again, assuming we can measure both of those angles and this distance here, we have an angle, side, angle problem, right? Again, angle, side, angle. So now we can look at solving for our distance h here. All right, again, this is why we have an angle, side, angle problem. Okay, so first off, we start by we can solve for side C here. All right, by again, just doing 180 minus the two angles that you already have. So we get C as in C is in a value of 75. All right, and then very simply here, what we can do is we can then just use our normal law of sines. So we've got our 60 feet here over sine of 75. And since we're dealing with h, we've got to be dealing with this 40 degrees angle. So we have h over sine of 40. All right, we multiply by sine of 40 to get it to the other side. And then again, depending on if you're asked for exact or to calculate, you will get a height out here. Okay, so I will let you guys practice with law of sines on your own here. But again, the difference being obviously different equations, but the type of information that you have. So is it an angle, angle, side? Is it an angle, side, angle? Right? What's the difference here? Okay, so summary of those types of problems here, okay? So if you're dealing with a side, side, side problem, you're gonna be using cosine. Right? You're gonna be using cosine, and you're gonna be using the alternate form of the law of cosines. If you're dealing with a side angle side problem, you're going to be using the standard form of the cosine or law of cosines. Okay, and then for law of sine, if you have a side angle angle or an angle side angle, you'll use law of cosines, right? If you have an angle angle angle, right, A, you'll also sorry, we'll get to that in a second. Sorry. If you have a side side angle, all right. Oh, I don't know why they introduced both of these here. Okay, so apologies, but so these are the only three that we talked about in this unit. And for some reason they brought these up here. These are cases that you actually can't solve at this point, and they shouldn't be asking you to solve for this in anything moving forward. All right. Because for here, this is an angle, angle, angle. All right. Well, no matter their size, they're gonna have the same angle. All right. And this is gonna be looking at similar triangles. So basically, since it's gonna have an angle, angle, angle measurement, all right, whatever one side of this is, it's gonna dictate the other two sides. All right, and it's gonna work for multiple answers because again, the point of similar triangles is that they'll have the same angles and the same ratios of lengths, obviously dependent on what is your major length there. So that one's a little bit difficult to solve. And then this last one here, side side angle, is what they call an ambiguous case because it may have 0, 1, or 2 solutions for the different sides and the different angles, okay? And we'll look a little bit here at this next one. But the reason that is because, of course, depending on the value that you have or the value that you choose, it could then have a domino effect on later values, okay? And so looking a little bit more at this, okay? Looking a little bit more at this. It's described again, of course, as a side-side angle. All right, so we have our side-side angle. All right, so using our law of sines here, side-side angle, we're looking at angle A. Okay, so if we have this ambiguous triangle here, all right, we can then first solve for angle B here. All right, we can solve for angle B here. And the reason this becomes ambiguous is because when we're looking at B, we could have as many as 2 answers or 2 triangles that fit the values given, right? And you've seen a lot of that again with our unit circle, right? So if we were looking for sine of 1/2, right, there's 2 places where you could have sine of 1/2, right? It could be a positive and a negative, or it could be a negative and a 2 positives, right? But there could be as many as 2 answers, or there could be no answers that fit that triangle. All right, and perfect. So looking here, of course, if we were looking for sine of A, right, again, whatever this A value is, okay, it's found in 2 places here. It's found in 2 different places. Okay, so again, there would be 2 answers for this angle of B. All right, one answer would be this acute angle, right, B1, and one angle would be this obtuse angle. All right, but they both have values that could be equal to sine of A. Right? They both have values that could be equal to sine of A. So when we calculate them, the 2 solutions will have, will look like this. All right, will look like this. So once we've calculated B, right, you also need to calculate the second value of B. All right, and what that's going to be is that's going to be our 180 minus B. Okay, so assuming that this is B1 here, we also need to calculate our B2 value. Oops, sorry, too far. All right. So if the values for B, A, and A are such that sine of A is equal to 1, then there's only going to be one answer, right? There's only one place where sine is equal to 1. All right, so then that's going to be a 90-degree angle. All right. If there's a value for B where it is greater than 1, right, on our unit circle, we have no value that sine of A or sine of B is going to be greater than 1. Okay, so if that happens, there's no solutions for your angle. Okay, there would be no solutions for that angle. All right. If A is greater than or equal to B, if A is equal to B, then there's obviously only one solution, okay? And they would both be acute angles. If A is greater than B, okay, if A is greater than B, then that makes A an obtuse angle, all right? And it makes your triangle look shifted like this, okay? And again, this is helpful for knowing because when you are given values, right, if you're just given values, you can use this kind of knowledge here to help draw your pictures, all right? And one key thing to remember here with these is that there can only be, in a triangle, there can only be one obtuse angle, all right, if there's even an obtuse angle. Right, but there can only be one obtuse angle in a triangle. So if this is the case here, that A is got to be greater than B, all right, then that would make A an obtuse angle, and that would shift your triangle to look something along this line here. Okay, and if A is greater than B, right, when we solve for B, remember we had 2 potential answers, right? We had 2 potential answers depending on what the value we're looking for is, okay? So if if that's the case here, remember, when we were solving for B, right, it gave us two angles, right? It gave us one in quadrant 1 and one in quadrant 2, right? So it gave us an acute angle and an obtuse angle, right? It gave us an acute and an obtuse. So if this is the shape of the triangle, since we know that B has got to be less than A, B has to be the acute angle. So it would be the answer that's in quadrant 1. Right? It would be that answer that's in quadrant 1, right? Because it's got to be an angle that's less than 90 degrees. Okay, it's got to be an angle that is less than 90 degrees. All right, perfect. Since we know it's got to be the smaller acute angle. Got to be the smaller acute angle. All right, here summarizes, right, the ambiguous SAS cases. All right, so again, these are the most difficult cases that you'll run into because it requires a lot of logical thinking here. All right, it requires a lot of logical thinking. So again, what is going to happen is you're going to have to look at the different sides. All right, and figure out what is the length of the sides and what's their relationship. So again, you've got three cases. If A is greater than, or sorry, if A is less than B, if A is equal to B, or if A is greater than B. All right. And then of course, if A is less than B, you could have two solutions, one solution or no solution, depending on the value of what we're trying to solve for, okay? If A is equal to B, there's only one solution since it's the same angle, all right? And if A is greater than B, there's only one solution, and you're dealing with, of course, the acute solution because it has to be less than 90 degrees, okay? Again, more practice problems. Please make sure you at least do these because, again, the ambiguous problems are the most difficult in my personal opinion because it requires that extra logical step once you're done with it. Okay. And then finally here, they're giving you they call it a real world application. Since we're talking about aliens, I'm not quite sure, but you know, a real world application is this thing called triangulation. All right. And what it is used for, first off, the definition of it is to find a location of an object based on measurements from two other locations. Okay. So basically, triangulation is you're making a triangle based on two observations, or two objects, right? So Alice and Beatrice here, we know that they're 100 feet apart, and they both are looking at the same thing here, okay? And we can see here that Alice points one arm at Beatrice and her other arm at the UFO, and she measures an angle. So Alice has an angle of 25, while Beatrice has an angle of 35. All right, so this would be an angle, side, angle, triangle. All right, an angle, side, angle, triangle. All right, so using this here, we can figure out what our distance, or sorry, what our third angle is, and then of course the goal is to figure out our distance between the two people, right? So using our final angle here, we can calculate our length A and our length B, obviously using our law of sines and the corresponding angle depending on which one you're solving for, okay? So again, an extra step just being making sure you have your picture, understand what you're asking, and understand what you're looking for. All right. And then the final kind of steps here. All right, so looking at our law of sines, okay, of course, this is going to be our law of sines, so we can say sine of A over A, sine of B over B, or sine of C over C. Or obviously, we've seen it more the other direction there. All right, but basically, the ratio is got to be the same. All right, it's got to be the same. So sine, 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 they're all on top, and the the distances are on bottom, or the other way that we've seen it more casually. All right, but regardless, the ratio between them is going to be the same. All right, and the law of sine works for all types of triangles, right? Acute, obtuse, or right triangles, okay? That the ratios are still got to be the same. All right, we worked through a couple problems here. Again, knowing the difference between asking you for an exact answer versus to calculate the answer. And again, realizing what triangle you have, right? Do you have a side, 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 side angle, side angle, 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 side angle, 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 or SSA, so side, side angle, okay? And for each of these types of problems, okay, it's asking you to determine if it's possible to know all of them, right? And obviously on that review sheet, it talked a lot about, okay, well, which one are you going to use? Are you going to use the law of cosine or the law of sine? And basically figured out that our SSS and our SAS use our cosine, our side angle, angle, and angle side angle use our sine, and so does this final one here, uses our side angle, of course, with an extra step depending on what the lengths of our triangle look like. Okay, of course, what the lengths of our triangle look like. Okay, so that kind of summarizes that guy. And then taking a second to look at, obviously, our checkup problems. Of course, here's our law of sines or our reciprocal, right? They both can be used as long as you're consistent, right? And then it's going to deal a lot with practice problems. So first off, of course, identifying what type of triangle you're dealing with, right? Identify what type of triangle you're dealing with. Again, side, angle, side angle, what are you doing, right? And solving for that. And then, of course, the last ones here are dealing with the ambiguous side and side angles. So draw them out. That's going to be my biggest key for you, is draw them out and then write what information you have. All right. And I would try to make this relative. So if A is 5, it should be longer than our side B here. Right? If A is 5, make it longer than B, or opposite if B is greater than A, right? And what this is going to do here is you've got to use that information. Knowing A and B, it's going to tell you, are you going to have solutions? Are you not going to have a solution? Or are you definitively going to have one solution, right? So that's all dependent on the relationship between A and B here. Okay, and then problem 10 deals with that triangulation, right? So figuring out the coordinates based on 2 observers. All right. So that kind of wraps up our lesson for today. So just to give you a reminder here, we introduced ourselves to Unit 5, which is applications. Okay, today you're responsible for 5.1, which has 1 quiz, and 5.2, which has 1 quiz. Okay. Again, go through it, do at least the practice problems within the study, try a couple checkups before you get here, because we only have these 2 quizzes. Then tomorrow, of course, we'll finish up with 5.3, talking about this thing called vectors, and then we will wrap things up and talk about, obviously, the test for this, and then that finishes Unit 5 for us, okay? So that will finish Unit 5 for us. All right, so if you guys have any questions, let me know. But you've got those 2 quizzes today. You'll have another tomorrow, including a unit test. All right, so get to work. Like I said, reach out when you've got questions. I'm here to help. Have a good day, and I'll see you guys tomorrow, though. Bye-bye.